Let's look at another example of this flip and slide technique applied to continuous time signals. This time we're going to look at an example coming out of a communication system problem. So we'd like to be able to manually compute these convolutions using the five-phase method and interpret the output signal and interpret the behavior of the system that we're analyzing. Okay, so suppose you're measuring a radio transmission S of t, which has been corrupted by some interference at a particular frequency f0. So, basically like you have some sort of tone, like a beep, which is kind of interfering with your signal S of t. So to cancel it out, you could try to implement a filter that, say, integrates its input over a fixed window of time. So the question is, what would happen at the output when you see that? So if you're doing any kind of finite length filter, you're going to have this sort of five-phase and a finite length signal, like a finite length beep, for example. You're going to get this five phases of convolution, and we can interpret those as being nothing happens until the receiver gets this signal, this interference signal. Then there should be some transients from, say, a cosine starting at that frequency f0. Then there'll be some steady state behavior, and then some transients as the signal ends, and then eventually the signal should go back to 0. So these are the five phases of convolution. So the actual signal is S of t plus x of t, where S of t we can think of as being the legitimate signal. So let's actually just focus on the interference signal x of t. And we want to get a mathematical model for that. So we want to model a beep of a finite length. So let's make our life simpler and take two integers, m and k, where m is smaller than k. And we're going to make a beep of length k over f0. So here we're going to have this cosine 2 pi f0 t. That's a beep of infinite time. And then I'm going to clip it. I'm going to clip it between 0 and k over f0. And why am I doing that? So that I get a integer number of cycles in that time period. And then h of t I'm just going to define as a box from 0 to m to m over f0. So this convolution h star x is going to show us what is the effect of this filter h on the interference. So of course the first step on any problem is to draw a picture. So here's a picture of our cosine. Here's a picture of our box. That's our filter that we're going to apply to this cosine. So let's look at phase 1. There's no overlap, and the output signal is 0. So the box, remember this point here is t, and this is t minus m over f0. It's important to remember that, and we're going to be sliding this box along. So when we enter phase 2, there's some partial overlap. And remember, we're going to go from tau equals 0, and then this is tau equals t. Right? So we're integrating from 0 to t, and we're integrating this cosine, 2 pi f0 tau, times the box, but the h is just 1, so it's just cosine 2 pi f0 tau, d tau, and we get sine. Integral of cosine is sine. So that's hopefully pretty straightforward. And that's going to happen all through phase 2 until the box is completely inside the cosine. So here you have the complete overlap case. And still, at this particular moment when t equals m over f0, this sine actually equals 0 if t equals m over f0, right? Because then we get 2 pi m, and m is an integer, so sine of 2 pi m is 0. Okay, so now in phase 3, we have this total overlap. That is, the red thing overlaps completely over the blue thing. And so remember, we're going to have this is t, and this point here is t minus m over f0. So we're going to get an integral from t minus m over f0 to t. We're going to integrate the same cosine, because remember, the h of t is just equal to 1. And so now we're going to get the sine, but we're going to get the sine evaluated at these two limits of the integral. So we get a sine 2 pi f0 t, and I get minus 2 pi f0 t minus m over f0 from the lower limit of the integral. But if you just multiply this out, we're going to see we get sine 2 pi f0t minus sine 2 pi f0t from this term here, minus 2 pi m, but this 2 pi m is an integer multiple of pi, 2 pi. And so this phase shift, we can just remove it because it's an integer multiple of 2 pi, and we're going to get sine 2 pi f0t minus sine 2 pi f0t, or 0. So in phase 3, the steady state behavior, if you like, that we talked about at the beginning, the steady state behavior is in fact 0. You'll get 0. So that's kind of what we wanted. We wanted to cancel out the interference. Okay, so again in phase 3, we're sliding along. We're going to keep getting 0 because as we slide through, we're just going to keep getting an integral from. We're going to evaluate this sine 2 pi f0t and then this integer multiple of 2 pi phase shift, and so we're just getting this thing minus itself, or 0. Okay, in phase 4, the box starts to leave, and again remember this is t, and over here is t minus m over f0. And so what is this point here, though? This point is where the integral is going to end, and this is k over f0. That's the length of the beep. So we're integrating from t minus m over f0 to k over f0. We're integrating this cosine. We're going to get sine 2 pi k. That's going to be equal to 0. And then we get minus sine 2 pi f0t minus m over f0. We again have this integer multiple of 2 pi here, which we can get rid of. So we're getting minus sine 2 pi f0t is our final answer. And so we get another little beep coming out of this signal. And then in phase 5, we have no overlap, and the output signal is 0. And it continues to be 0 as we slide on and on. The box no longer overlaps with our beep. So putting it all together, we have that the signal is 0, then it's a little bit of transient in a sine, then 0, then transient of a sine, and then 0. And we can write down the limits where all these transitions happen using the 5 phases of integration. And so this is a visualization of what the output looks like. So this doesn't look so great because this period here where I cancel out the interference is kind of short. But let's try and take a look more generally, because we've proved a very general formula for how this system works. So the output has 2 sinusoidal transients and a dead period. If k is much larger than m, then the transients are going to be short. So we're going to cancel out most of the interference. So instead of looking like this, we're going to have like this, dead period, and then like this. That's sort of what, that's kind of what we hope it would look like, right? And so this dead period would be quite long, these transients would be short, and then we've canceled out the interference. So we're done, right? Great, we made a system that canceled out the interference. But hang on a second. This filter is actually going to distort the legitimate signal. So remember, we had s of t plus x of t. This was the interference, which is bad, but this is the legitimate signal. And this is we want to keep this, but now we're going to be computing. We're going to also have s of t star h of t. Right? If I take this thing and I convolve it with h, I'm going to get s of t convolved with h of t, and this might not be so good. Right, so this filter is going to distort the legitimate signal. And so this raises the question, well, how is the best way to get rid of a beep? So one thing you could think about is if its f0 is kind of far away from any other action or useful stuff in s of t, you could use something called a notch filter. which is essentially a filter which is going to zero out a particular frequency component in the input signal. But we haven't gotten the chance to design these kind of notch filters yet. That comes later in the course. So, what we can do with the tools that we have is build this kind of system which can cancel out some of this type of interference for us at the expense of doing a little bit of, I guess you can think of it as smoothing of the legitimate signal S of t. So why don't you try for yourself to see if you can get some sort of five-phase convolutions going. You can look at a case where you have a decaying exponential clipped at 2 points, convolved with a box. You can have some sinusoids convolved with boxes as we had before, and you can also look at the ramp function clipped off, so we get a ramp up to time 4, and then convolved with a box to see what you get there. And writing out these, looking at the limits of the integrals and then doing the integrals, you'll sort of get some practice at doing these five-phase convolutions.